Now, without any further ado, we're going to go ahead and introduce Brett Hall, who is going to talk a bit about his WAkka library for being able to use computational expressions for creating Akadana actors. Brett, how are you doing?
I'm doing all right.
Good. All
So,
right. Well, why don't Gregorius and I go ahead and duck out here? And we actually, well, I guess we could go ahead and stay on the stream, but we'll give you an opportunity to give your presentation and show what you've been working on to the other Akadana users.
all right, great. Thanks a lot. Yeah, so I'm Brett Hall. I'm a principal software engineer at a company called Wyatt Technology. In a few slides, I'll talk about what we do. But anyway, we built this new library we call WAkka. Um, W is for Wyatt, since we developed it at Wyatt Technology. Um, and I'm bad at coming up with names for things. So um, anyway, it kind of stuck. So what is it? It's a new library for creating actors. It's built on top of Akka.net. Here's a couple of links: GitHub and NuGet. I'll put these links up again at the end. Anyway, so all right, Waka. What is it? So it heavily, well, it's an F sharp specific library. It heavily uses a feature of F sharp called computation expressions. So apologies to the C sharp folks in the audience. I don't know if you can actually use, like, when we compile the computation expression stuff into an assembly, I don't even know if you can use that from C sharp. I'm not terribly experienced with C sharp myself. I'm pretty much come to .NET entirely from the F sharp side of things. Um, if you can use them from some C sharp, I bet they're really painful to use because you don't have all the syntactic sugar that the F sharp compiler gives you for dealing with computation expressions. So this talk's going to be all F sharp. Um, and yeah, maybe it'll motivate some of you to switch sides. Anyway, so WAkka, we developed it at Wyatt Technology. So a little bit about us: we're a manufacturer of analytical instruments, primarily used these days in biotech and pharmaceutical industry. Um, and just so you know, kind of where I'm coming from and what we get out of Akka. Um, we aren't doing big cloud deployments or distributed computing or anything like that. We're primarily using Akka.net for concurrency management. We deal with a lot of concurrency in our applications. Like, we're dealing with multiple data streams coming from multiple instruments. We're running calculations in the background and getting results, input from the user in the UI, um, and all of that stuff. We've got to manage all the concurrency. Uh, and then also resiliency. So we have situations where our customers, they spend like $100,000 preparing some sample that they're doing research on. Um, they put it in the instrument. If our software crashes halfway through, like, the 4 hours it takes to collect the data, they're going to be kind of angry because their sample's wasted. And it's going to cost them a lot of money to make more. So we try and use the resiliency and Akka.net supervision hierarchies and all that to be able to recover from crashes and continue and get all the data we can. So customers don't lose massive amount of money because we crashed. Um, so things we're not concerned with right now: system scalability. Like I said, we're not doing distributed computing. Our stuff either runs on a single desktop computer or on the instrument itself, which is very limited environment. Um, that may change in the future, but these concerns are kind of, when I talk about the design of WAkka and some of its drawbacks, which everything has some drawbacks. Um, they're kind of driven. The design decisions were driven by this. This is very much a scratch your own itch kind of library. So at the end, I'll discuss whether this is the right thing for you. Okay. So what motivated me to make this library, which I haven't actually told you what the library is yet, but first let's get into some motivation. Um, so in F sharp, when you're using Akka.net, there's sort of three ways right now to make actors. Um, there's kind of just the same way you do it in C sharp, using the object-oriented stuff and deriving classes and all that. There's what are called effects, and there is a computation expression that you can use to build F sharp actors now. But I'm going to get into a little bit of why I don't think it's terribly useful and what motivated me to build WAkka to effectively replace it. Okay, so first off, if you're just going to use the object-oriented way of doing things. You just like in C Sharp, you would derive a class from one of the Akka.net provided base classes. So here I have some sample code. So this is just for an actor that you can send a message. It's just basically a key value store. So you can send one of these messages. You can send a query to get the value of a key, and it will send the value to whatever actor reference you give it here. Or you can update the value. You give a key and a value, or you can tell the actor to shut down. So in F Sharp, this is how you go about deriving a class. So first you declare your class type storage actor. We inherit from untyped actor. I'm just keeping this simple. Um, F Sharp's a little more pedantic about downcasting things. So to get the context, to get the actual context as an I actor context, I have to use this downcast operator here. Oh, and actually, I'm moving my mouse all over the place, and you guys probably can't see that. That may be the drawback to uploading my slides. Um, so actually, Aaron, I think I'm going to switch to sharing my screen real quick so that I can actually point to things, if that works for you. Oh, still there, Aaron?
My microphone was muted. Yes, go right ahead.
Oh, okay. Let me make sure I'm in the same place.
Now, while you're
Go
doing
back to
that,
using.
one question I had for you is for your resiliency work you did
Hmm.
at Wyatt. I guess you use Akka.persistent? Oh, sorry, these are still your slides, aren't they? Yeah, sorry
Yeah,
about that.
yeah. Hold on one second. I'm still getting my screen
Yeah, no
shared here.
worries.
Yeah. So for resilience, yeah, we're using Akka persistence. Why is it?
While you're doing that,
Um,
Brett, I might answer
yeah.
this
Sorry, I'm
question
trying to.
real. All good. I'll give you a second to do that. I'll answer this question real quick. Is there a tutorial somewhere for a typical business CRUD application with Akka, like web API, validation, DB access, all done with actors? Yes, there is. I haven't done, let's say, a full-blown like web eShop or something where I'm doing stuff like integrating user accounts and access control lists and all that stuff. But I do have a sample that uses CRUD with integrating ASP.NET, Razor pages, and Akka.NET with cluster sharding and all that together. And I'm going to drop that link in chat right now, which you can go ahead and see. But if you have some feedback on that, please go ahead and leave a comment. All right, Brett, I think I can
Okay.
see.
Yeah, you can go ahead and share that screen, and I'll make that screens. Oh, wait. Sorry, the perils of technology here.
All good.
All right. Can you see my slides? Okay.
Right now, I can see your desktop with a.
Uh, okay. It's not behaving like I want it to. Let me see here.
No worries. Well, as I said this morning when I was doing a training with a customer, I said, of all the hard problems in computer science, making conferencing software that doesn't suck is very high on the list.
All right. Let's see. Hmm. Maybe we'll just have to go back to the slides. I can't figure out how to make it show Keynote in full screen.
Oh boy, well, I'm sorry about that.
Yeah. It's my fault for deciding, hey, let's use this new button here. All right.
No worries.
Anyway, okay, so jumping back into where I was. Okay, so in the sample code, there's type storage actor, you inherit untyped actor, and then the context, I was just casting it because F Sharp's a little pedantic about that. And then there's this let mutable values map empty string. So that's the actual key value store. Um, in F Sharp, everything's immutable by default, so you have to put this mutable keyword on here if you want to be able to modify things. And then I override the on receive um, method, receive the message, and these things with the colons and question marks is a casting operator, um, which does a dynamic cast on the object. And if it's a storage message, great, we go through. If it's a query, we get the values, send it back. If it's an update, we update our values, and if it's a stop, we stop the actor. Um, so this is basically just this like a C# style actor, um, uh, just translated into F#. I guess the only thing would be the storage message where I'm using discriminated union types. That would be harder to do. You do that differently in C#. You probably just have classes for each type. Um, anyway, so you can do just the C# way in F#. It's not the most idiomatic way to do things, but it works. So the next thing to try would be using what are called effects. And so for doing F#, you can either use just straight Akka.net. There's an F# variant of Akka.net. And then there's another library called Awkling, which is basically just the F# version of Akka.net, except for the actor references are typed. Like it has a basically it has a generic type parameter that says what type of message you can send through that actor reference. And I like that. So we've been using the Awkling library ever since we started using Akka.net a few years back. Um, but anyway, with effects, what you do is so the stub at the top, the response, and the storage message are the same. But now we have some function that starts the storage actor. We call Awkling spawn with a parent and a name for the actor, and then you have properties. And the properties, you have to pass it a function that will be given the actor context, and it has to generate what's called an effect. An effect is just it's a change to the actor state. Um, there's a few different kind of built-in effects, but what we're going to do here is we have our message handling function, and we're going to use the effect become, which is the very last line down here. And we pass it the function we want to use to handle messages. And this one, you can see my handle messages takes two arguments, the values and the message. Whenever I pass it to become, I'm actually baking in whatever the current state of the actor is. So when we start, it's an empty map, you can see on the last line. But then if we go into handle messages, uh, this will be called every time a message comes in, the message will be passed to it. And in this case, when I declared it, I made the actor context an actor of storage message, so it ignores all messages except for storage message, so I don't have to do all that casting. Instead, I'm just passed a storage message to begin with, and I can just do a match on it. And the queries, everything's about the same as before. Query, um, you look up the value and send it back to the receiver. You can see that if you get a query message, um, so this handle messages has to return an effect. In this case, we're returning the ignored effect, which basically says, I'm not going to change my state based on this message. I'm effectively ignoring it, even though we didn't really ignore it. We sent another message in response to it. Um, and then update, we update the values, and then we do become. Again, we handle messages is going to be our message handling function. But now the new values, the updated value map, is passed to handle messages so that we have the new values. And then finally, if we get a stop, then we return the stop effect. And this is mostly when I'm not before WAkka, this was how I was mostly making actors. And I mean, it works fine there. I'll get into some of the frustrations I had with it in a minute. But finally, there's also what's called using computation expressions. Again, both the akka.f# and the Awkling libraries provide this. Instead of explicitly using the become and ignored actors, instead you use this computation expression. Now you can see the handle messages function. Um, it uses the Awkling computation expressions actor computation expression, um, and that is another way it generates an effect. Um, but now we explicitly call it context receive to receive a message. Um, we have to use match exclamation mark because the context receive returns a special kind of value that has to be handled by the computation expression. Anytime you see an exclamation mark in a computation expression, something special is going on. Um, so we receive the message, query, again, we just send back the result. This time, instead of saying ignored, we just call handle messages recursively with the same values. We don't change the values. The update looks almost exactly the same, except for doing this return exclamation mark handle messages with the new values. So that's going to update, or that's effectively the same as saying become handle messages new values. Um, for stop, we still have to say stop because that's how you stop the actor. Um, but this is almost, I mean, there's very little difference between this and become. Over here, I say it's isomorphic just because I'm trained as a physicist, so I use a lot of math terms. Anyway, uh, so there is a computation expression already, but in a few slides, I'll get into why it's not terribly useful and there's not really a reason to use it um, instead of just using these effects directly. Um, and that's because computation expressions, while they're powerful, they do have drawbacks. I mean, the first thing is just you have to, there's a certain cognitive load. You have to think about what does let exclamation mark do exclamation mark match exclamation mark. They do, depending on what kind of computation expression you're using, they do different things. So that's something you have to worry about. Um, and then also, this is all the computation expression syntax is syntactic sugar for a bunch of function calls and continuation passing and all this stuff that's going on behind the scenes. And when you're stepping through in the debugger doesn't see your original code. It sees the desugared code, basically the code that the compiler converted it into. So if you try and step through a computation expression, it'll jump all over the place. And the variable names will be different in the watch window. Um, the variable names used in your regular code generally won't be in the watch window. You have to figure out which variable goes with which. So there are drawbacks, and usually you need a really solid advantage, at least in my opinion. I don't know if everybody agrees with me on this, but in my experience, you need a solid advantage for using the computation expression over regular code. Like it needs to really be helping you with something to make it worthwhile. And this computation expression just doesn't, well, maybe I have another. Yeah. So this computation expression just does not do that for me because it's basically the same thing as using the effects directly. Um, so here's another example. Usually you want your computation expressions to be composable. And so this example here on the left is from using a library called F sharp or FS toolkit error handling, which if you're doing F sharp, you should be using this library. It's great. It makes your code much easier to read when you're dealing with results and options and things. But there's a type in F sharp called result. It has two cases, okay, some value, error, some value. Um, and if you don't use if you aren't using a computation expression, then you have to do a lot of match your result. If it's okay, then do another thing, and you end up with these horrendous, like, um, nested matches if you got to deal with more than one value and they're in different result objects. Um, and the FS toolkit result computation expression hides that from you. Basically, if we look at this last one, add numbers, the let a res equals a bunch of stuff. Um, the right side is a result. If it's okay, then if it evaluates to okay, it takes the value out of the okay and binds it to a res. If it's an error, then it just stops and the whole result computation expression, its value is just that error. So it just skips the rest of it. So you don't have to have a bunch of if else's and matches and things. You just do this and it just automatically short circuits for you. And so that's really useful in itself because this is a lot more readable. Um, but also it's composable. So you can see I extract an A res and a B res from two, um, in this case, options that requires some function that I'm using here, takes an option, and if it has a value, then it makes it okay. If it doesn't have a value, then it makes an error with this string that I put here. Um, so if A and B both have values, they'll be bound to A res and B res. And then I can pass those to add, and note add also does a result computation expression. Um, because it's going to use this parse function to parse the string into an integer, and then I'm going to add them together. And you can see I can return a value plus b value. Um, so I can basically return a value and use it with this let bang binding here. Um, Now, if I want to do something similar using the computation expression in Awkling or the Akka F sharp library, I can't do that. So here I want to create a function that filters messages for me. Like it'll receive messages. If I get a string or a double, if the message can be cast to a string or a double, then I want to be able to return those to the code that called filter messages because I found a message I care about. If it's anything else, then I just recurse and just keep waiting for what a message that's a string or a double. So I want to be able to create a function like that and then call it from within another actor here. Down here I've got print message. I wait for a filter. I call filter messages to get my message, and if it's a string or a double, I define a type to wrap the result in. I want to do that, but you can see I've got red squigglies everywhere because the actor computation expression has to evaluate to an effect, and effects, um, you can't really return an effect and do anything with it. Like I couldn't return like an effect that wraps this string or the double, because the effect has type object and that's the message type. There's no way to return some other value. Um, Basically, you always have to evaluate to an effect and give that effect back to the actor system to go and um, deal with another message. So that was really frustrating to me because that's different from every other computation expression you work, or most other computation expressions you work with. So, I mean, to deal with this using regular Akka, you basically need to build a state machine. You first become the state that waits for a specific message, then you become a state that prints out the message. In this case, this is a really simple example, but I didn't mean to put this pun in here, but all these becomes very cumbersome, and hard to follow for what I'm going to term workflow code, where you're going through a lot of different states, and the state flow maybe gets complicated and isn't just a simple do this, return. It might flow in all sorts of different directions. Um, so I made WAkka, and so here's the first example of WAkka code. On the left, we have my example of what I want to do with the computation expression, but it doesn't work. So on the right, it's almost the same code, but it does work. So the differences are, so filter messages, instead of the Akka F sharp or Awkling actor computation expression, I'm using WAkka simple, and I'll get into what simple and other types of actor expressions mean in a bit. And so in the uh, computation expression here, first thing I do is I say I want to receive a message, and I'm receiving any message. So this is just going to give me any message that comes in. It's just going to return it as an object. I cast it. If I can cast it to string or double, I return it wrapped in this other message discriminated union type I have at the top. If it's anything else, I just recurse and wait for another message. And so then I have this filter actor down below. Again, this is just regular. So WAkka has its own spawn functions. And in this case, we pass a parent, we pass properties, and I'm doing a named actor instead of anonymous. The not persisted, I'll talk about what that means in a bit. And then I have an actor computation expression where I call filter messages, wait for the result, and the result, I get either the string type or the double string S or D case of my message. And this works great. So a minute ago, I mentioned what I call workflow actors. And for some reason, I don't know if it's the field I'm in or what, I end up having to do a lot of actors that I've dubbed workflow actors. Um, and what that means is that it's an actor where you do some stuff like, you send some messages to other actors or interface with some other system or something. And then you have to wait for some messages. Once you get those messages, you do some more stuff. And then you wait for some more messages, do stuff. This repeats to some amount, and then at the end, you're kind of built up some result, and you send that result somewhere. One thing to note: these waiting for messages, we might be waiting for different types of messages each time we wait for messages. The other thing is often whenever we wait for messages, there's some other sort of class of messages we also have to watch for and deal with. It might be, I mean, most of the time it's something like a cancel message coming because user hit cancel in the UI to stop whatever process is going on. Um, but we also want to be able to watch for those easily. So with standard Akka ockling, this ends up being just a mess of state transitions, and it's really hard to follow. With Waka, it ends up just looking like a linear function, maybe with some extra function calls you have to look into, modulo some funny keywords with exclamation marks on them. So that was the big win, and I'll give an example after I've kind of explained the structure of a Waka actor. I'll give an example of code like this. So alternatives, if you're building actors like this, the alternatives are, extensive use of ask, and that's always a bad idea. Um, and the problem is ask, you can't handle these other like if we're looking for like a cancel, we also need to look for a cancel message in addition to whatever we asked for. You can't do it. I try and avoid using ask so I can never remember if ask just ignores other messages until it receives the response from who you sent the ask to, or if it um, stashes and unstashes. But I mean, regardless, ask, you're just asking for trouble if you use it. I'm sorry, I'm saying too many puns here. Um, there is like become stacked, and things like that that allow you to basically stack up like where you're going to return to, um, when you do state transitions. This works great if your control flow is stackable, but if you're like you got like some general state machine that's going to branch and continue somewhere else depending on what kind of messages it gets, or some other information, um, then that tends to break down, and then you end up passing continuations through, if you're using effects, become, um, if you're doing sort of C# style stuff, there's other ways to set what your message handling function is, or you just track the state and have like a switch or something. Um, but this becomes painful and hard to follow, and that's what motivated me. A new product we were working on that hasn't been released yet, um, had a lot of, I was passing continuations around like crazy, me and the other guy working on it, and it was just, it was becoming really hard to follow, really hard to debug.
When
um
you when you talk
uh,
about
but,
continuations, do you mean like task continuations?
no, more like, just like callback functions,
Oh,
like
okay.
you'd pass it, like we'd get an actor where like when, so like you'd go to some state, but you'd have to give it some structure that had like four different possible like functions it could call to figure out what to go next. So effectively it is like a task. It would be like taking a task and saying continue with.
Gotcha.
um
Okay.
but we'd have to pass in like whole structures to handle the different things that could happen, because if it gets this message, then it's got to go do this, if it's got that, and it just became a nightmare. um so that led me to um, build Waka, and eventually I was able to convince the higher ups at Wyatt to let me open source it as well. Um, but how? Okay, so all right, so that's my motivation for Waka, mostly frustration and wanting to be able to simplify things, at least at the level of when you're writing actors. I mean, Waka itself gets a little complicated under the covers, just because that's how computation expression code under the covers tends to be like that. Okay, so now let's talk about what Waka, how you actually use it. What's the structure of a Waka actor? So when I showed that example before, we called a spawn function, and when you call the spawn function, you pass it an action, um, and that action is what is run in order to run the actor and handle messages and things. Waka itself provides many primitive actions, sort of the building blocks, and that's things like, oh yeah, sorry, did I? CEs are is generally the abbreviation for computation expressions in F#. Sorry if I'm
No
confusing people
worries.
with that.
I think he was
Okay.
responding to somebody else in chat, is what I think.
Oh, okay.
Yeah.
Sorry. I just see the bubbles pop up every once in a while. Anyway, so yeah, so you spawn, you have to give it an action. WAkka provides a bunch of primitive actions as building blocks, things like waiting for a message, creating child actors, stashing messages, persisting an event. There's a whole bunch of them. And then you combine primitive actions using an actor computation expression. I mean, that's the computation expression really is just glue for gluing together these building blocks. Um, and actions themselves have return types or have result types. They evaluate to something. And like if you wait for a message, it evaluates to the type of message you asked for, or if you just said, give me any message, it evaluates to an object, and that's the message it received. Stass a message just resolves to what's called unit, which is basically similar to void. Um, Persisting an event, the result of persisting an event is the event that you persisted. Um, but the actions, when you combine a bunch of actions, they don't all have to have the same result type. Um, and the computation expression allows you to glue them together and use their results to build bigger results. That's the composability that I was going for when I designed WAkka. Um, okay, so actions, they come in three types. They're simple, and simple actions, basically, simple actions, you can receive messages, so it includes the message reception actions, but you can't do persistence. Um, and then there's event sourced, which can't receive messages directly, but they can do persistence. They can persist events into the Akka persistence system. And as Aaron asked me earlier, we do at Wyatt, we use the Akka persistence system to handle like if the program crashes while we're in the middle of a data collection, we have another program watching it and restarts it, and it just uses the Akka persistence system to get back to where it was in the middle of a data collection. Um, so event source actions let you persist events, and there's a persist action that you give it a simple action to run, and whatever the result of that simple action is, it gets persisted, and then that's the result of the persist action. Um, so if you're doing an event sourced actor to receive messages, you have to do a persist action, and then within the persist actions sort of sub action is where you would receive a message, and if you're going to do something with it at the level of the persisted actor, you have to return an event. Um, And then also the persist action, if we're in replay mode, we're replaying events because we crashed, or just, you're just restarting the actor. Um, the persist action, instead of running its simple action, it just returns whatever event was persisted. And then there's, so we've got event source, simple actions, event sourced actions. And then we have common actions, which are ones that work in either context, whether you're an event sourced actor or not non-event sourced actor. All right, so there's three types of actions. There's also three types of actors currently. This may grow in the future. But there's not persisted actors, which just they run simple actions, and if they get restarted, they just start over from scratch right at the beginning. Um, there's no way of restoring the state if they crash and get restarted. There's checkpointed actors, and this is maybe not the best name because it's going to be confused with checkpointing in an event sourced actor. This has nothing to do with the event source checkpointing. This is basically it runs a simple action. If it crashes, instead of starting over from scratch, it starts over from the last message reception action, the last place you waited for a message. So you just lose whatever message you were processing when you crashed, but you get your state back. Um, that only works for an actor crash. If the whole process crashes, I mean, it's just done in memory. It's kind of like if you're using Akka persistence, but you don't configure it to use some kind of event store, and it's just storing things in memory. If you crash, you don't get your state restored. Um, or if the process crashes, you don't get your state restored. So this can't recover from a process crash. You can't use this persist actors and then restart them later and get your state back. And finally, there's event sourced actors. They run event sourced actions, and they replay persisted events if restarted. So this can recover from a process crash if you've configured Akka persistence appropriately. So that's a lot of verbiage. So let me give a couple of examples here. So first off, to build a not persisted actor. So this is again the sort of key value store actor example I was giving before for the other ways of creating actors. We've got a response type, we've got a storage message type. And so come in here, we have our start storage actor. You pass a parent to for creating the new actor. We use the WAkka spawn function. We give it the parent. Um, we give it default props, and I'm naming the actor here. There's also a WAkka common props anonymous that you don't have to pass a string to create an anonymous actor. And this creates just the default properties you would normally get. If you use the default properties in Akka, you can also um, uh, you know, make changes to that if you want. This is a not persisted actor, so we use the not persisted function to start the actor here. And this actor is expecting a simple action. Um, so we're going to have our handle messages function here, which uses the WAkka simple actor computation expression. So that's for gluing together simple actions. um, and so it tries to receive a message. And here we're using receive only because we only want to receive storage messages. It will just filter out any other messages that come in. Um, and you can also this function, you can also pass it a strategy for what to do with messages. By default, it just ignores them. You can have them be stashed and then unstashed once we get a message. Um, or you can define your own custom behavior if you want. But anyway, so we receive a storage message, we handle it. If we get a query, we send the result to the query receiver, and you'll notice I do. So in the example before using effects, um, there's this operator that is the left angle bracket exclamation mark. That's the message send operator from Awkling and Akka.f sharp. In WAkka, we redefine it so it creates a message send action. And if it's an action, if you want it to run, you have to it either has to be bound in a let or do or return with an exclamation mark. And we do that because if you use the operator from Awkling or Akka F sharp, and you use it in the wrong spot in a computation expression, it'll send the message when you don't expect it to, because it's not an action, and actions non-action code can if it precedes any other action code, then it'll when you're constructing the computation expression, it'll run that code immediately um, uh, instead of when the actor is actually running. Um, that's actually sort of a bug. I thought I had worked out all those bugs, but it can still happen. So instead, we overload that operator ourselves, and you have to do this do here. But the action run sends the message, and then it recurses, calling itself again with the same values, so the values didn't change. Update is pretty much exactly the same as what we had before. We do an update on the map to get the new values, and then we call ourselves with the new values. And stop is slightly different. There is a WAkka common action stop action, which will stop an actor, and that's useful like if you've called into a bunch of functions and um, you want to stop the actor just wherever. But if we're at the top level like this, we can just return. In this case, we have to return unit. Um, uh, oh, oops, I'm on the wrong. Oh, I jumped slides. Okay, so we could return this common action stop, or we can just return a value. In this case, the not persisted is expecting an action whose type is unit. So we can only return the one type of unit, which is empty parentheses. But that ends the actor. If you hit the end, it returns a value. That's the end of the actor computation expression. And it in this case, because it is the top level and was the thing that was passed to not persisted here, the actor ends. Um, so again, this actor, if for some reason this actor crashes, it will go back to here where we did handle messages map empty. So you won't return. There's no state retained. If it's when its parent restarts it, it'll go back to the very beginning. Now, if we use a checkpointed actor, we'll get the behavior that it will restore the state. And the only change you have to make is to use WAkka spawn checkpointed instead of WAkka spawn not persisted. Those are between the previous slide and this one, that's the only change. And so this actor, you get a message from the WAkka simple actions receive only. If you crash while processing that message, it will effectively just jump right back to where you were there, and the values will be the same. Your values map will be the same. Um, but again, that only works as an actor crash. If the whole process crashes, you're out of luck, and you can't use it to do to persist actors and restart them later and get their state back. To do that, you need an event sourced actor, which will work a little differently. Um, so here I still have the same response and storage message, but now I've added this type event. So there's an update event that has a key and a value, or a stop event. And so where do we use those? If you go over to the right, we've still got our start storage actor function. We do a spawn, again, pass the parent, same default parameters, the name, but now we do WAkka spawn event sourced as our sort of our actor start function. And event source expects an event sourced action. Um, and for now, let's jump past this wait for message and go down to the handle messages function. And you can see this one uses the WAkka event sourced actor computation expression instead of the simple actor computation expression. So this generates an event sourced action. And within an event sourced action, we can use the persist action. Here I'm using persist simple. There's also an action called persist, um, which I'll talk about that in a second. Persist simple, we give it a simple action. It executes that action. Whatever the action evaluates to gets persisted into the Wyatt persistence system, and then that event is returned. So we're going to match on that event. So if we look at wait for messages now, we see that this one uses the Wyatt simple actor computation expression. So this is going to be a simple action. Um, it does what we did before. We wait for a storage message to come in. If it's a query, we send the result, but then note that we recurse and call wait for message again. So that's not going to persist anything. That's just going to send the result, and we're going to go back to waiting for another message. Um, but if we look at update and stop, update returns an update event with whatever the update value is. Stop returns a stop event. So if we go back to handle messages now, we do persist simple. It runs the wait for message. We're going to get an update event or a stop event. So here, the update event, that's where we update our map, and then we recurse call handle messages again with the new value. If we get a stop event, we just here return unit, which stops the actor. Um, but now, if we crash, or if we, you shut down the process, whatever, you start it back up and you restart this actor, the persistence system kicks in. It says, oh, I've got events. It replays those events. So persist simple, every time it gets called, instead of running wait for message, it just returns whatever, the next event from the persistence queue. And so those will most likely, there'll be a bunch of update events so that you'll update your values until you get to the end of the event stream. And then you'll go back to calling wait for message and receiving messages and everything, and your state will be all the way back. If the actor stopped, we persisted a stop event, so we're going to see, a stop event, and if stop event and stop the actor. So I mean, to me that seems a pretty simple way to do the persistence, deal with the Wyatt persistence system. So persist simple, like I said, this is simple. All it does is it persists a value, returns it. If it encounters any sort of error, like Wyatt persistence error, it just kills the actor, just stops it and logs an error. There's another action that's just persist, which has a more complicated return type. It isn't just the value that was returned by its action, by this simple action. It's a discriminated union that can tell you things like you got a persistence error, replay is finished, things like that. But it's more complicated to use, so didn't include it here. Okay, and then so before I was talking about workflow actors, this is an example of how you do a workflow actor with Wyatt. So here I've defined a couple of messages, message A, message B, and the thing I'm calling sent message. So I'm saying, okay, so there's a function here. We're going to run a workflow. We have an actor that we're going to send our result to, or no, sorry, no, we have an actor we're going to send messages, the sent message type to, and it's going to be an event sourced actor. And so this, I'm just defining the actor action, You could spawn this into, you could use spawn to spawn an actor that just did this, or you could have another actor, event source actor running, and you could just call this function to run this as part of that actor. It'll just come in, it'll do these actions, and then it'll return back to that actor to let it continue doing whatever it was doing before. So again, it's an event source actor. So this is an event sourced action. Um, so the first thing we do, we're doing a persist simple. We do a simple actor. We're going to send a message, sent one, to this send to actor, and then we're going to return the result of waiting for a message A. So if we get a message A, then it's going to persist that message and return it to the event sourced actor. Um, and then we do something similar in the next step. We're going to come in here, we're going to send another message to this other actor, and then we're going to wait for a message B to come in. We're going to persist that message. Um, and then at the end, we're going to take whatever the value of A and the value of B are, and concatenate them into a string and return that string. So if we called this from another actor, the result of running this run workflow action would be some string with these things concatenated. Um, so this is a lot simpler. If you were to do this with effects or object-oriented WAkka or Akka, you'd be doing a lot of state transitions to do this stuff. I mean, this is a very simple thing. I often write these things that go on for like 100 lines of
This
code.
is very concise compared to what it would take in C sharp, where you would need to have basically, yeah, like two properties that would need to be set inside this behavior. Each receive method for message A, message B would have to check to see if the other is set. And when
Mhm.
only when both of them are set would you be able to produce your return value. And that would be a significantly
Yeah,
larger amount of code than this. So this is very
and
slick.
yeah, this is what I this is making actors like this is the only reason I put the time in to make Waka. If you're just doing an actor that spins in a circle, receiving a message and updating a state and never not doing like big state transitions and things, or trying to do a like a linear workflow like this, then effects or the object oriented Waka, they work great. No complaints. But once you start doing stuff like this, it just gets really difficult to follow. Um, so yeah. Um, all right. So yeah, so this is kind of the killer app for this. But now, of course, there are caveats. Any library is going to have trade-offs. So first off, event sourcing. So there's that checkpointing actor, which has nothing to do with event sourcing, and checkpointing for event sourced actors is currently not supported. Um, I have an idea of how to do this. It's just again, I'm not do I when we use persistence, we're using it to recover from crashes. We generally aren't doing persistence on actors that run for like a year at a time or something, or are going to generate enough events that checkpointing is really useful. So I just have kind of punted on this. At some point, just out of interest, I probably do it because I have an idea of how to do it, and I get ideas for things, and it bugs me until I get a chance to sit down and work on them. But it's probably going to involve either a new actor type or a modification of the event sourced actor type. But I'm pretty sure. I mean, this is doable. It's just haven't had the time or energy to deal with it. Um, there's the usual. Oh, there should be computation expression caveats. So there's the same ones I mentioned earlier. There's a cognitive load of understanding how the computation expression works, and basically, if your team isn't used to using computation expressions, and you're the person introducing this, you will answer a lot of questions. I think on the project I was working on with one other guy, he was new to F sharp and he was new to Akka, so I was answering a lot of questions anyway. But once I introduced Waka, I was introducing a lot of I was answering a lot of computation expression questions for 2 or 3 weeks and then at some point something clicked with computation expressions. When you start working with them, you'll be confused a little bit, and then once you've got a little bit of experience with them, something clicks, and it's second nature. But if you're the person who knows how to use them and other people are new to them, you will answer a lot of questions initially. And then just the usual debugger issues. I mean, it's syntactic sugar and it gets desugared, and the debugger sees the desugared code. So stepping through will be a little confusing. Um, And finally, performance. So I did some not terribly scientific benchmarking. There's a project in the source tree called performance test. It just does a basic ping pong between two actors, you know, times how long it takes to send like 100,000 messages or something or more. Well, actually, it's got to be more because I was sending because of these timings. But anyway, you send some set number of messages between the actors and time how long that takes. Um, so it does it using the object-oriented method, using Ockling effects, and using WAkka. And for using the classes or using effects, I was getting about 1.5 million messages per second on a newer M1 MacBook Pro. Um, Using WAkka, I was only getting zero 0.9 million or 900,000 messages per second. For us, that's still plenty of performance. If you are handling, you're writing actors that need to have maximum throughput because you're getting you're hammered with millions of messages a second. You may not want to use WAkka for that. Um, that's why I say WAkka is currently not appropriate for all workloads. Also, I mean, since I made it, I'm like, oh, this is neat. This is my new thing. I've been using it for everything, but the debugger stuff with computation expressions makes me now feel like if you're just doing an actor that just doesn't do state transitions, it just processes messages and maybe updates a state, just like state values, or doesn't even do any state. Um, Using effects or just the classes might be better, just because if you have to debug through that, it's easier. Um, but you do lose the ability to like back here when I was doing this thing where I just have a function that you can just call and it basically integrates directly into your actor. You run you run this little workflow here, and then you go back to your regular actor. Um, that would be the thing you're giving up. You wouldn't be able to do that easily. Um, but back to performance. There's probably performance optimization to be done, but like I said, 900,000 messages a second is way more performance than we need for our purposes. So again, this is mostly scratching my own itch. Um, I do kind of like performance optimization sometimes, so if I have some time at some point, I'll probably start messing with it. But there could also be just a kind of a systematic thing here where I don't know if you're familiar with F sharp. There's a couple of computation expressions. There's the async computation expression for doing asynchronous computations, and there's a new task computation expression which also does asynchronous computations, but it does it as sort of TPL tasks, whereas async you can run it as a TPL task, but it isn't really that. And async was sort of defined or designed for IO bound computations, and task is more meant for computation bound computations, for lack of a better term. Um, and the big difference is, so task, they had to add some new machinery to the F sharp compiler, which instead of the normal way, the original way of doing computation expressions, that basically builds a little state machine, which makes it really fast, but you lose tail recursion optimization. Um, which again, if I go back to say this example of the storage actor, we're recursing a lot here. If we don't have tail recursion, after you go through a couple thousand messages, you're going to blow the stack. Um, so it may be, oh, oops, it may be that this performance just can't be remedied entirely. Um,
One
so that's something I may look into at some point. But
one question I have about the
mhm,
performance using the Akka.NET
yeah.
classes, is that using the built-in F sharp API?
No, so that was like basically, if I go way back here, uh, what's my first example? Basically, it's doing like inheriting from untyped actor,
Hmm,
um, and just doing on receive.
interesting. So I was gonna say when I do benchmarks for like individual actors on, I'm using like a 5-year-old Gen 1 Ryzen machine,
Hmm.
and the number I get for untyped and receive actors is in the ballpark of between like 4.5, like up. It's a little bit high. It's a lot higher now on .NET 7 if you have like PGO
Uh-huh.
enabled, but the historically
Well,
for a
this,
long time it was like 4.5 million.
yeah.
Um,
Well, I mean, I will say one thing. I'm back on .NET 5, even though
oh,
I know
okay.
it's been deprecated. but the upgrade cost from Visual Studio 2019 to Visual 22 for the entire team has not been surmounted yet. So we're kind of stuck with .NET 5 for the moment. I'm chomping at the bit to go to .NET 7, both for a variety of reasons. But I mean, I use Rider, which I bought myself, so I have to be
That's
careful I don't break things for everybody else. Um,
I also use
yeah.
Rider as
So
a
and
leader.
and and again, our use of Akka, everything is plenty fast for our purposes. We aren't again, we're not don't have some public API on the internet that's getting hammered by billions of messages a second. So um, I may not have structured thing the most performant. Um, if someone is looking for a fun little performance optimization thing they can look at and see if they can get that number up, I guess. Leave it as an exercise for the reader. I was just mostly looking at comparative, and even if you're getting 4.5, then that makes Waka look even worse. So um, yeah.
I was mostly wondering
Okay.
if it was the F sharp sort of like layer between Akka
Uh, I
and all
don't.
that that
I
might be
think so.
doing that.
I mean, I didn't look at like the compiled IL. Like if I were to implement the same like actor just deriving from untyped actor, um, if I were to say write it in directly in C sharp and compile both and compare the IL to see if they're doing something different, it might be because I know there's a lot of things the C sharp compiler does that the F sharp compiler doesn't do. I think on that level, um, to optimize things, but I'm not sure. I mean, the Ockling effects. I mean, who knows? That totally different thing. I mean, under
Yeah.
the covers, it's also deriving. I mean, Waka under the covers, we're deriving. We have an actor derived from untyped actor, and it's basically just running the continuations that are generated by the computation expression to handle messages. Ockling, I think, does something similar. I've looked at the source code before, but it's been a while. Okay. So yeah, that's Waka. Again, the GitHub and the GitHub and NuGet URLs here. And then there's me. I'm GitHub, just Brett Hall. I have a blog that I write on once every couple of years. The most recent thing was a post announcing Waka, and it has more examples along the lines of what I talked about here. You can find me on Twitter for the moment. Who knows what's going on there. And then I've also signed up for Mastodon just in case, so you can reach me there as well.
Well, thank you very much, Brett. I got to say, this is definitely the most active I've ever seen the chat room. And any of our community stand-ups so far. I guess we got to get
Oh,
the F sharp community
no,
involved
I
more
can't
often.
see it, so hopefully they're saying nice things.
Well, there was a raging debate about abstract syntax trees and computation expressions, and I saw the word
Yeah.
monad flying around in there. So
Well,
uh,
yeah, that's the dirty secret of F. You're not supposed to use the M word around computation expressions, but that's what they are. I gave a talk at um, the last Open F sharp before the pandemic hit on, and I was allowed to use the M word. I think I was the first person ever allowed to use the M word at that conference for something similar, not walk up as something similar. So let's see. So someone's asking if we have support for cluster sharded actors. Um, I don't know. I've never used cluster. Again, I don't do big distributed stuff, so I've never used cluster. I barely even used Waka Remote. Just played with it, so I don't know that I can answer that. It doesn't directly. So there is one caveat that I left out. In F sharp, you can use code quotations to basically write an actor on one actor system and then send it to another actor system to be run. Currently, Waka does not support doing that. If you're using Akka remoting, you need the actors defined on both sides, and you have to jump through some hoops. I think I've gotten it working before, but again, that's something that probably needs to be looked at as well.
well, for cluster sharding, I think as long as you could get there's basically a bit of code to start the shard region where you have to basically
Hmm.
specify it's a little function that takes the identity of like an entity actor and then returns props that can be passed into the actor of method. As long as there is some
Yeah.
way one of Waka's actors could be fed into that, then I think you should be okay actually.
Yeah, I think that sounds similar to what I did when I was playing with remoting. Um, it involves changing some of the yeah, you need to do some of the properties different when you start the actor. Tell it where to start.
Let's see. I brought Gregorius back into chat here. Gregorius, did you have any questions for Brett?
No, it everything went over my head. So yeah.
I really liked the way you defined your workflow and that sample there. I thought that was a very clear cut example of where Waka solves a problem better than Akka.net's sort of more, I guess, built inherently object oriented approach does.
Mhm.
I could see the clear business value there. Now, if you actually wouldn't mind going back to that real quick, I had some
Sure.
syntax questions for you, just because I'm not
Let's see.
all.
This one?
Yes, that one,
Yeah.
perfect.
Okay.
So, in fact, I'll go ahead and squish us down into the out of the frame here, and let me see if I can figure out how I can hide that current comment. There we go.
Yeah, hold on.
And
I did something here.
that might have been me,
There we go.
actually. I
There.
might have moused over it while I was using my middle mouse button. Um, so my question here is, technically, is this let expression for message A and message B, are these starting like additional actors under the covers? Is that what's going on here? Or
No,
okay,
no. So I mean, basically, when you have a computation expression, when you have a let expression, basically what it does is it evaluates what's on the right hand side um, is evaluated, and behind the scenes when you define the computation expression, this Waka event source actor thing is of type actor builder. Waka event source to actor builder. I forgot what I called it. It's there's a class that's associated with this. This is an instance of that class. Um, and one of the methods on that class is called bind. And this is where you get into the monad stuff. So I'm going to try and not get too deep into that. But basically, this let, so it evaluates the right hand side and it passes the result of that to bind. And then the second argument of bind is a function that takes whatever the type of message A is, um, and basically wraps up the rest of the computation expression in that function. So it's basically like we evaluate what's on the right hand side of let bang message A equals, and then we call a function where we're passing whatever the value of that is to the function that generates the rest of the code in the computation expression. Um, and so basically what Waka does is when it hits one of these lets, oh, let me see if I get this straight. It gets a little confusing. But basically, it's like it's generating so it's going to run these things. When it gets to a receive, it's going to generate a continuation, and it's going to go back to the actor and it's going to go back. And so on receive, it's just been running whatever these actions are. And when it gets to a point where it needs to receive a message, it returns and waits for the next message. But it's set in the state of the actor is set the continuation, basically the rest of the code to pass the message to run to generate the next continuation. So none of this is starting new actors. It's all just one actor. It's just a lot of basically figuring out what we need to do after we receive a message, storing that in the state, and then waiting for a message. And then we do all the stuff until we hit another wait for a message. And when we get there, we figure out, oh, okay, this is the continuation once we receive a message, and then it on receive returns. Um, and it effectively just goes in a loop like that.
gotcha. Oh, very cool. Well, I'm hopefully a whole bunch of people. So we had a whole bunch of positive comments like this one in chat from people who stuck around for the entire hour and 15 minutes so far.
Oh, yeah.
So
Sorry, that took longer than I thought it when I practiced it.
no, not at all. I think people were really engaged and definitely enjoyed it. So hopefully you'll get some people installing your library, and if you start seeing GitHub issues show up complaining about things, that's how you'll know they
You're
care.
gonna come and fix them for me?
Dude, no siree. Um,
Yeah. Yeah.
but that's how you'll know that that people are really giving it
Oh
the good
yeah.
old college try.
Yeah,
Uh,
and I will say, I mean, so this library was, it was built for what we do. There's probably rough edges. when other people start using it. So definitely if you run into rough edges and say, hey, this piece of functionality I like is missing, file issues, I don't know if I'll have time to get to them, but hopefully, especially if they're interesting to implement. Let's see. So there's an alien to the fourth power here is asking, does it matter whether A or B is received first? In this case, it does, because we're using the default version of receive only. It ignores messages that aren't message A. So if message B comes in first, it'll just go off into the ether and be ignored. And then when you wait for message B, it won't. If message B and message A were only sent once, you'd be stuck. In this case, I'm kind of assuming that message A was sent because we sent one to this other actor, and message B was sent because it's sent two. Like when I'm doing this, usually it's because the messages I'm sending are like commands to send commands to the instrument to like set the laser power, and then I'm waiting for a state update message that shows the laser power was set to what I asked it to be set for. Things like that. Yeah, I didn't mention we shoot lasers at things at my work. So